The event horizon is often misunderstood. It is not a physical surface or a solid wall. Rather, it is a precise mathematical boundary in the fabric of spacetime. At this specific distance from a black hole's center, the geometry of spacetime becomes so severely warped that all paths lead toward the singularity. This boundary marks the point of no return. Here, the escape velocity required to leave the gravitational influence of the black hole exceeds the speed of light. Since nothing can travel faster than light, nothing can escape. Even light, the fastest entity in the universe, finds its trajectory bent inward. Once past this threshold, all possible directions in space point only toward the center. Falling into a black hole subjects an object to extreme tidal forces. This phenomenon, known as spaghettification, occurs because the gravitational pull at the feet is significantly stronger than at the head. For stellar mass black holes, tidal forces are lethal almost instantly. However, for a supermassive black hole, the tidal gradient is much gentler, potentially allowing an observer to cross the event horizon unscathed. Once inside the event horizon, the geometry of spacetime undergoes a fundamental transformation. Outside, we move freely in space and time flows forward, but inside, these roles reverse. In the extreme curvature beyond the horizon, the radial coordinate r behaves like time. Just as you cannot stop the flow of time in the outside world, you cannot stop moving toward the singularity inside a black hole. The singularity is no longer a physical place you can avoid. It is a moment in your future. Every spatial direction you choose leads inexorably toward the center. Movement toward the singularity is as inevitable as the passage of time itself. You are not traveling to a destination, you are arriving at the end of time. At the heart of every black hole lies the singularity. It is a theoretical region where space-time curvature becomes infinite and the density of matter peaks at an unimaginable scale. General relativity, our best theory for gravity, breaks down here. Its mathematical equations produce infinities, signaling that the theory can no longer describe the physical reality of the core. This infinite point serves as a placeholder for a future theory of quantum gravity. Here, we believe the smooth fabric of space-time is replaced by discrete, quantized fluctuations, where the known laws of physics must be entirely redefined. The information paradox represents a fundamental clash between our two most successful theories, general relativity and quantum mechanics. Traditionally, it was thought that anything falling into a black hole was destroyed, its history erased from the universe. Modern physics suggests a different view. Black holes may act as quantum hard drives, scrambling information and encoding it onto their surface rather than destroying it. This requirement that information must be conserved is the cornerstone of modern quantum information theory. Solving this paradox is the gateway to understanding quantum gravity. The information paradox has long troubled physics. If a black hole evaporates, does the information inside vanish forever? The page curve suggests that entropy must eventually decrease, preserving quantum information. The breakthrough is the island formula. It states that the black hole's interior, the island, is holographically encoded in the Hawking radiation emitted outside. By applying quantum extremal surfaces, we find that the interior information isn't lost. It is scrambled by the black hole's dynamics and then carried away by radiation, ensuring the universe's total information remains conserved. Black hole complementarity addresses a major tension in modern physics, the conflict between the perspectives of an outside observer and an observer falling into the black hole. To the outside observer, information appears to be scrambled and preserved on the event horizon. This holographic view suggests that nothing is ever truly lost, just stored on the surface. Conversely, the observer falling in experiences no wall or high-energy barrier at the horizon. They continue their journey into the depths, maintaining the equivalence principle of general relativity. Complementarity posits that these two versions of reality are different but mathematically consistent. Both accounts correctly describe the physics within their respective reference frames. Studying black hole interiors directly is impossible, as no information can escape. However, we observe the shadow they cast against the surrounding glow of accretion disks and photon rings. When two black holes collide, they produce gravitational waves. The final stage, known as the ring down, emits a unique frequency that acts as a fingerprint for the event horizon's behavior. While the interior remains hidden, the fingerprints left on surrounding spacetime allow us to test the laws of gravity and quantum mechanics with unprecedented precision.